All right, let's look at a few probability calculations applied to civil engineering. And that is this notion of recurrence intervals, these extreme or rare events. So let's talk about or try to calculate some things here. What is the chance of at least one 50-year event happening in the next 50 years? Remember here that X can be defined as the number of events that we have in those Y years, and that X gets drawn out of a binomial distribution. We're going to have 50 trials, one for each year, where on each and every year we have a 1 in 50 chance of then seeing that event. Right? So we're looking to find out what's the probability that X is greater than 1, that we have more than one of these particular events in the next 50 years. Right? And so, hey, it'd be a lot easier to deal with this as the complementary event, right? We could go find out the probability that X equals to 1 and 2 and 3 and so on all the way up to 50, or we could just go 1 minus, that'd be the total probability, minus the chance that we don't have any at all. And that's the far easier thing to calculate here. So that's the binomial distribution, 1 minus that binomial coefficient sitting over here. That's 50 factorial over 0 factorial, 50 factorial, right? And then we take our success rate, that'd be 1 minus the 1 over 50, and raise it to the 50th power in this case. And then we have the failure rate, 1 over 50, raised to the 0th power. That we have, what this says is that we've got a coin that has a 1 chance in 50 of coming up, or a die, and 1 chance in 50 coming up with our magic event, and we have 49 chances that we don't. We keep rolling that thing 50 times, and we want 50 of these coming up as not happening. And that just amounts to then there's a 63.6% chance that we'll have at least one 50-year event in the next 50 years. Also means that we have about 36.4% chance of not seeing that. That's basically 2-to-1 ratio here between whether we will or won't see the n-year event in the next n years. It is not certain that we'll have it, right? Before we go to the next calculation, again, I want to emphasize something. The 50 shows up in 2 places, but they have 2 different meanings. The first one says the 50-year event. That's telling us the little p-value, the probability of success or failure, 1 over 50, right? The other one is setting how many flips of the die are we going to look at, or flip of the coin rather, or roll of the die that we're looking at. So that second 50 is showing up there and there. It also will show up here. This is going, if this was 40, this would be 50 minus 40 or 10 or something like that, right? There's an n minus kind of thing going on up in that one, right? So that number taken associated with that one is going in the reciprocal part right there, right? So let's look at it slightly differently. What's the chance of a 50-year event in 2 consecutive years, right? So the chance that it happens in 1 year is 0.02. That's just really straight definition. And then year 1 and year 2, well, they're independent years, so basic event probability says intersection of this and this event, we multiply those 2 together, they're independent, so there's no overlap in the Venn diagram space of, or to subtract out. And that's going to be your 0.02 squared, or about 4%. Well, what if we had a 50-year event in year 1 and a 50-year event in year 3, but that obviously means not in year 2? What's that probability chance? Right, so that's the intersection of these 3 events. And again, if they're independent, then we just do a straight multiplication of those, and we'll be slightly less than we were before. That's at 0.039%. So those 2 numbers look an awful lot similar, and from practical purposes, you'd really say they're about the same, but they're not. If we were talking about a 10-year event, then this number would change. It'd go down to 0.9, that would go up to 0.1, and that could begin to have a much more significant difference between that. This would, of course, become 0.9, or rather 0.1 squared, and etc. So, yeah, be a little cautious about just simply rounding those and saying they're the same number, and therefore there's no distinction. There is a very much a distinction between those. And then finally, let's look at this one. What's the chance of no 50-year event in 100 years? right? Well, that would be probability x equal to 0. Again, that's binomial, but now we're going to have 100 trials. So that changes these a little bit, right? But that likelihood of success or failure remains the same, just that we're doing more flips. And now our probability goes down to only 13% chance. It's still not that small, though. I mean, small might be like 1,000th of a percent, right? Well, that's not what this is. This is 13.3% chance. Now, another way we could do this is to say, well, for a 50-year event not happening in 100 years, it means the return period, the time between events, has got to be greater than 100. And now our rate parameter is the 1 over 50. And we can work out the exponential distribution, and we get nearly an identical value. The reason why they're not the same is, of course, this is a counting kind of process. This is a continuous variable process. So there's a discretization that's in essence happening here. And this is the continuous domain version. But these numbers are going to be very much the same. And to the point that we actually like to use this one down here much better or much more frequently because it's just easier to work with.